Good afternoon, class. We are looking at section 6.3 logarithmic functions and 6.4 graphs of logarithmic functions. So we covered exponential functions, graphs of exponential functions, and now we're going to look at logs. The objectives are to convert from log to exponential form, convert from exponential to log form, evaluate logarithms, use common logs, use natural logs, identify the domain of a log function, graph log functions. And so to remind you, when we looked at the exponential functions, we went over exponential rules from zero exponential rule to the product rule, quotient rule, all the way to negative exponential rule, and you name it. Then in order to graph an exponential function, f of x is in the form of a to the power of x. A, the base must be positive. A can't be 1. And it's a continuous function. So first and foremost, what happens when a is 1? It's not an exponential function. It is a horizontal line. When a is between 0 and 1, it's an exponential decay. When it's larger than 1, it's an exponential growth. It gives rise to the following. HA, horizontal asymptote, is the x-axis in these two cases, which has the equation y equals 0. There is no vertical asymptote. Y-intercept in both cases is 0, 1. X-intercept doesn't exist. Domain in both cases are real numbers and range from 0 to infinity. 0 is not included. When a is positive, you say it's increasing or an exponential growth. And in that case, as x goes to infinity, so does y. The limit of f of x as x approaches infinity is infinity. And in this case, as x goes to negative infinity, the limit of f of x as x goes to negative infinity is 0, which gives rise to the horizontal asymptote y equals 0. When a is between 0 and 1, in this case, it's a decreasing function, an exponential decay. The limit of f of x as x approaches infinity is 0. As x goes to infinity, y goes to 0. And the limit of f of x as x approaches negative infinity is infinity. So as x goes to negative infinity, y goes to positive infinity. That's the idea. Now we are going to look at logarithmic functions and graphs of logarithmic functions. So let's start with a definition. Consider f of x equals 2 to the power of x. Can a formula for f inverse be found? You're going to write y equals 2 to the power of x. Then we interchange x and y, and here's the inverse function. Therefore, f inverse of x equals y is the exponent, because we're going to solve for y, right? To which we must raise 2 to get x. Let us define a new symbol to replace the words, the exponent to which we must raise 2 to get x. Log x base 2, and we read it as follows. The logarithm base 2 of x, or log base 2 of x, means the exponent to which we raise 2 to get x. Thus, if f of x is 2 to the power of x, then f inverse of x equals log x base 2, or log base 2 of x. However you want to read that. You have to mention base with number 2. Note that f inverse of 8 is log 8 base 2, which is 3, because 3 is the exponent to which we raise 2 to get 8. In other words, class, 2 cubed, we know it to be 8. So if somebody asks you, what is log 8 base 2? You have the same answer for the exponent 3. In other words, the question is as follows. 2 to what exponent gives you 8? It's the same as writing log base 2 of 8 equals what? Both answers are 3. So pretty straightforward, everybody. Let me erase that because I need this space. Convert from exponential to logarithmic form. Let's see how we do that. That's a pretty straightforward process. X is b to the power of y. So y is the exponent. B is the base, so y equals log x base b. So to understand this better, and I hope you remember this from intermediate algebra college, and now with college algebra, we emphasize this with more details. If you look at the following arrow that I give you, b to the power of y is x, and that's all there is to it. B to the power of y is x. As long as we remember this, we should have absolutely no problem. Just pay attention to the arrow. Just pay attention to the arrow and you'll be fine. All right. Let's just follow this arrow. By the way, sometimes we use base A, base B. It doesn't matter as long as we understand this means b to the power of y is x. So over here, we want to be able to go back and forth. We want to write this in logarithmic format. So we want to go from here to the left in essence. So this is log of 15 base 7 is x. So log 15 and the base is 7 equals x. Or log to the base 7 of 15 is x, however you want to mention that. Now this one, remember the base is pi and the exponent is 3. So log m base pi is 3. Over here the base is x, the exponent is 5, so log 12 with base x equals 5. And in all of these cases, if you go this route, you can see the exponential form. In fact, for the following, we're going to write 3 to the power of 4 is x. Log x base 3 equals 4. 3 to the power of 4 is x. Log 5 base x is 2. X squared is 5. Log 8 base 3 is x. 3 to the power of x is 8. All right, let's look at the graph of logs. For any real number, a must be larger than 0 and a can't be 1. And x must be larger than 0, then y equals f of x equals log x base b. Base a is a logarithmic function. Remember, the same restriction that we put on exponential functions, a must be positive, a can't be 0. And x represent the argument of log, and it must be positive. So we are going to graph y equals log x base 2. To do that, let me write this is equal to y and go with the arrow and write x equals 2 to the power of y. Now, when we look at this case, ask yourself, which one is easier to pick and calculate the other one? Is it easier to pick x and calculate y, or is it easier to pick y and calculate x? Clearly y, so let us pick a value for y. Let's pick up a few values. We're going to go from -4 to 4, easy numbers. For example, -4, it means 2 to the power of -4. Just as an example, is 1 over 16. I hope everybody knows that. Minus 3, 2 to the power of -3, 1 over 8, minus 2, 2 to the power of -2 is 1/4, -1, 1/2, 0 gives you 1, 2 to the power of 0. 1 gives you 2, 2 gives you 4, 3 gives you 8, 4 gives you 16. So those should be easy numbers we should have no problem with. So if we plot those pairs, for example, negative 1 over 16 and negative 1 over 16 and -4, 1 over 8 and -3, and so on and so forth, all the way to 16 and 4, it looks something like that. Just pick up the pairs carefully along the x and y axis. Obviously, the easiest one would be 1, 0. You notice that here. 2, 1 is not too bad. 2, 1. 4, 2 is not too bad either. 8, 3 is not too bad either. They may be a little bit more difficult, but you can locate them. What do we notice? X-intercept at 1, 0. There is no y-intercept. Domain from 0 to infinity, range all real numbers. We don't have a horizontal asymptote, rather we have a vertical asymptote, which is the y-axis or x equal to 0. Needless to say, this is an increasing function. So if you compare these to an exponential function, you see that in the case of an exponential function, we had a y-intercept at 1, 0. Now we have x-intercept. There is no y-intercept. Domain from 0 to infinity. Range from negative to positive infinity. Everything goes from negative to positive infinity. Vertical asymptote, the y-axis, which has the equation x equals 0, and it's an increasing function. So let us compare the two functions, the exponential and logarithmic functions. So this is the graph of y equals a to the power of x. This is the graph of y equals log x with base a. In both cases, a is larger than 1. So y equals a to the power of x, y equals log x to the base a are inverse functions for a larger than 1. Their graphs are symmetric about the line y equals x. So as we look at what we had done with the case of exponential function versus logarithmic function, again, x-intercept none, this one y-intercept is not. Y-intercept was 0, 1, right? Now x-intercept is 1, 0. Domain for the blue one is all real numbers. The range is all real numbers. The range for the blue one from 0 to infinity, and in the case of the red one from 0 to infinity is the domain. We have a horizontal asymptote, which is the x-axis, which is y equal to 0. But in the case of a logarithmic function, we have a vertical asymptote, the y-axis x equal to 0. And both cases are increasing functions, y equals x. Let's graph y equals f of x log x base 3. We are going to write this as x equals 3 to the power of y. And therefore, we pick a value for y first. Let's pick up a few numbers. So if I pick negative 3, 3 to the power of negative 3 is 1 over 27. Negative 2, 3 to the power of negative 2 is 1 over 9. Negative 1, 3 to the power of negative 1 makes it 1/3. 0 makes it 1. If I pick 1, I get 3. If I pick 2, 3 squared is 9. If I pick 3, 3 cubed is 27. I'm assuming nobody has any problem with this basic evaluations. And now, if we graph this pretty carefully, okay, y equals log x base 3, it looks like that. And I wanted to emphasize the fact that logarithmic functions and exponential functions are inverse of each other. So y equals log x base 3 and y equals 3 to the power of x, same base. These two are inverse functions, therefore symmetric with respect to the line y equals x. If it's y equals log x base 5, then it should be 5 to the power of x. If it's log x base 7, it should be 7 to the power of x. Evaluate the logarithmic expressions. Again, this definition makes a huge difference. So the idea is that 3 raised to what power is AD1? So if you said, okay, let's set this equal to some variable, okay, for example, y, and then you go this route, you get 3 to the power of y is 81. And you know 81 is 3 to the power of 4, therefore y must be 4. So pretty straightforward. If we look at this one, and let's say this is x, 2 to the power of x is 1 over 8. We know 8 is 2 cubed. So 1 over 2 cubed, or 2 to the power of negative 3. Therefore, x must be negative 3. Example 6, determine the domain of a logarithmic function where f of x is log base 3 of x minus 2. In general, you set the argument. This is called the argument of log. Must be positive. And clearly x is larger than 2 or from 2 to infinity. G of x is log base 2 of x plus 3 over x minus 1. Same situation. the argument, whatever it might be, in this case, x plus 3 over x minus 1, must be positive, larger than 0. Needless to say, in this case, as always, the denominator can't be 0, therefore x cannot be 1. So, how do we deal with that? We go with the sign graph. If you set the top equal to 0, you get negative 3. You put the, so if you set the top equal to 0, x is negative 3, and the bottom is 0, x equals 1. Those are the points that we are going to do with the sign graph. On a sign graph, we have a number line going from negative to positive infinity. We are going to put these two numbers. X is minus 3. I'm sorry here. X is minus 3, everybody. Thought I mentioned minus 3, but I put 3. So minus 3 and 1, we must put it in order. At negative 3, this expression is 0. At 1, it's UD, undefined. And so you pick up a test point in between. Obviously, the easiest would be 0 between these two, minus 4 here, and let's say 2 here. These are TP, short for test points. So what do? We are testing the value of, when I say we test the value, we test x plus 3 over x minus 1. So I want to make sure that we understand that this is actually f of x, everybody. We are calling this expression g of x. Okay, we're calling this expression g of x. And so what's happening to g of x? Because this has degree 1, this has degree 1, they are all odd, they will alternate, so the easiest would be 0. If I put a 0 here, I get positive 3 over negative 1, makes this one negative. They will alternate positive and positive. However, if you want to just pick up negative 4 and plug in, please understand, negative 4 gives you negative 1 up here, negative 5 down here, negative over negative makes it positive. If you plug in 2, makes the top and the bottom positive, we get positive. So what are we looking for? Larger than 0, and x cannot equal 0. Therefore, the answer is here and here, which means from negative infinity to negative 3, union 1 to infinity. That's the meaning of it. Negative infinity to negative 3 is because it's positive here. Union 1 to infinity. That would be the answer. What about log of absolute value of x minus 1? Remember, this expression must be larger than 0. Absolute, the argument of log. Absolute value of x minus 1 must be larger than 0. As you know, absolute value, it's always larger than or equal to 0. It can never be negative. When will it be 0? This will be 0 if x is 1. X minus 1 equal to 0. x equals 1. So if you pick any value, you get positive, except 1 results in 0, and we have to have a positive. So all real numbers except 1. From negative infinity to 1 union 1 to infinity. Again, an absolute value is always non-negative. That means it's either positive or 0. We want this to be positive. So whatever makes this expression 0 will be excluded. X equals 1 makes it 0, and we are going to, x equals 1 will be excluded. We are going to write minus infinity to 1 union 1 to infinity. Example 7, the function p equals 95 minus 30 log x base 2 models the percent p of students who recall the important features of a classroom lecture over time, where x is the number of days that have elapsed since the lecture was given. What percent of the students recall the important features of a lecture 8 days after it was given? And here's the source. Well, basically, we have to plug into this x equals 8. That's all we have to do. Now, log base 2 of 8, I think most everybody by now knows it's 3 because we know 2 cubed is 8. So it's 95 minus 90, which results in 5, which means only 5% of the students remember the important features of a lecture 8 days after it is given, if they don't study. And that is important piece of information for everybody. If we keep up with our studying, that won't happen. Natural exponential and natural logarithmic functions, the natural base e. The natural base e is an irrational number that serves as the basis for the natural exponential function and the natural logarithmic function. E is a irrational number, which means it continues indefinitely, 2.71828182845, and it continues indefinitely. If you stop here, you have to change the 2 to 3 because next to it is 8. So it's an irrational number that it continues indefinitely. The natural exponential function is f of x equals e to the power of x, where e is the natural base. Natural logarithms, or Naperian logs, in honor of John Napier, who first discovered logs, are logarithms with a base of e, the natural base. Notation: log x base e, we use ln x. So in the case of a natural log, we don't write log, we just write ln x, and we mean the base is e. Obviously, x is positive, and this is called the natural logarithm of x. F of x is ln x. X must be positive. So here's the natural log. If you look at these two, okay, this is looking at natural log. This is looking at common log. In the case of a natural log, we use ln. And therefore, x equals e to the power of y, and y equals e to the power of x, and y equals ln x are inverse functions. In the case of a common log, when the base is 10, y equals log x means x equals 10 to the power of y, according to the definition, okay, class? So y equals log x and y equals 10 to the power of x are inverse functions and symmetric with respect to the line y equals x. So it's pretty straightforward, I hope, class. These are the two most important logs that we use, base e as well as base 10. Example 8, graph f of x equals minus ln of x minus 2. Find its domain, range, asymptote, find f inverse, and use it to find the range of f. So first, we're going to start with y equals ln x. When you draw a log x with a base that is definitely larger than 1, it looks like this. So it doesn't have to be perfect, but that's the concept. Now, first I want you to notice we have, of course, this 1, 0. The next step is to take care of this negative sign. So we are going to reflect it. So y equals minus ln x, reflected about the x-axis. So this thing will go looking like that. And notice this 1, 0 remains, but for example, e comma 1, okay, becomes e comma negative 1, or 1 over e negative 1 becomes 1 over e positive 1, okay? So first, look at the easy point, the x-intercept. Finally, we are going to use this negative 2. That means we're going to shift it right by 2 units. So this thing, you're going to shift it this way. In both cases, as it is, the y-axis or x equals 0 would be the asymptote. As we shift it to the right, the asymptote becomes x equals 2. And notice what happens to this point. 1, 0 is going to move to the right, and it's going to go to 3, 0. So this one, the same thing, this 1 plus 2, notice 1 over e, and then we have to add 2, and that's the idea. So the x coordinates, we are going to add 2, 1 over e plus 2, e plus 2, and we keep it as 1 over e, or e as an exact answer. We don't want to write the approximation. And so at this point, again, 1, 0, 1, 0, now it's at 3, 0. As far as the intercepts are concerned, obviously we have 3, 0 as it's obvious, and there is no y-intercept. As far as the domain is concerned, remember, the domain is from 0 to infinity in those two cases. But here, as we shifted to the right by 2, the domain is from 2 to infinity. The range doesn't change in all cases, all real numbers from negative to positive infinity. The vertical asymptote was the y-axis in these two cases, but here is x equals 2. All right. Now, we want to find the inverse. Here's the function. We are going to change f of x to y to make life easy. The next step is to interchange x and y. So this becomes x, this becomes y. The next step is to solve for y. So we're going to get rid of this negative. If we multiply both sides by negative sign, this goes away. This becomes minus x. Now remember, think about this. Think about this. Let me rewrite so it makes it easy for you to see that. Think about this as log base e of y minus 2 equals minus x. And now go with this arrow. So e to the power of minus x is y minus 2. If you rewrite again, you really should not keep it as log with base e. You should keep it as ln. But this because we are starting, I just wanted to make sure you see that. And therefore, we get this one. I give it the name f inverse. And of course, move this negative 2. So I'm going to get rid of this and make it plus 2 on the left side. So y is e to the power minus x plus 2. And instead of y, I'm going to call it f inverse. Let me erase everything. So we got the inverse function, and we remember this was the graph for f of x equals negative ln x minus 2. And we remember, for example, the intercepts at 3, 0, y-intercept is a non-existent. Therefore, for the inverse, x-intercept for this one becomes y-intercept at 0, 3. And y-intercept, which is none, becomes x-intercept, which is not. So we should recognize that. And you should recognize this is the graph, or you can pick up more pairs to graph. And just to give you an idea, needless to say, symmetric with respect to the line y equals x. And also notice what happens to the domain, range, and so forth. The domain for this function was 2 to infinity. Now the range is 2 to infinity. The range for this function, the blue one, was all real numbers. Now the domain for the green one is all real numbers. Vertical asymptote was x equals 2. Now horizontal asymptote is y equals 2. See, for the green one. So we should be able to make these transitions. Okay? We should be able to make these transitions, everybody. Graph f of x equals 3 log x minus 1. Find its domain, range, asymptote, find f inverse, and use it to find the range of f. So we start with the basic function y equals log x. Remember, the base is 10, everybody. So it looks like a regular log. And so this is 1, 0. Okay. And the reason we have 10, 1 here, because it makes it easy to understand. In the case of a log x, remember, if you plug in 10, what is log of 10? 1, because the base is 10. Now let's go with log of x minus 1. That means this one, we're going to shift it to the right. And these 2 points are going to shift to the right. So notice, shift to the right by how many units? 1 unit, okay? So by 1 unit, 1, 0 becomes 2, 0. 10, 1 becomes 11, 1. So right here, if you plug in 11, 11 minus 1 is 10, log 10 is 1. So that's the point. It has shifted. Finally, we're going to multiply this by 3. That means we are going to stretch it by factor of 3 along the y-axis vertically, okay? Which means the y gets larger by a factor of 3. So this one, the y is 0, it doesn't change, but this one, the y is 1. So the x doesn't change, the y becomes 3 times that. Whatever this number is, 1 becomes 3. So notice, if you look at this point, now it's located at 11, 3. But the reason this one doesn't change because the y coordinate is 0. And of course, when we did the shifting, the vertical asymptote over here was the y-axis. Now it's x equals 1. And so to answer the intercepts clearly, we have x-intercept at 2, 0. We don't have a y-intercept. We want to answer domain and range and everything else. Well, domain goes from 1 to infinity, whereas here was 0 to infinity. Range is still the same, all real numbers. When I say the same as these two. Vertical asymptote, which was x equal to 0, now it's x equal 1. All right, for this function, we want to find the inverse, f inverse of x. Therefore, given f of x, let's change the name to y to make it easy to work with. Y is 3 log x minus 1. Interchange x and y. So this becomes x, this becomes y. And right here we have the inverse. However, we are going to solve for y. To do so, we're going to get rid of number 3. That means let's divide by 3, both sides. And now, it may be easier that I write the x plus 3 on the right so you see what happens. If you notice this is x over 3, and you go with the arrow and class, when we don't write the base is 10. So that means 10 to the power of x thirds equals the argument of log, which is y minus 1. Of course, we're going to work on that. But my point being, I want to show you how to go from logarithmic format to exponential format using the arrow process I showed you. And of course, negative 1 moves, becomes positive 1, and we give it the name f inverse. Let me erase my word. So y minus 1 is 10 to the power of x thirds. So y is 10 to the power of x thirds plus 1, and we give it the name f inverse. Now, recall that for this function in the previous page, we got the x-intercept of 2, 0. Now we're going to have a y-intercept of 0, 2. And y-intercept is none, now x-intercept is none. Okay, so x-intercept is 2, 0, becomes y-intercept 0, 2, because it's an inverse function. So this was the graph of the y equals 3 log x minus 1. And this becomes the graph of f inverse, which is 10 to the power of x over 3 plus 1. And let's discuss the domain and range. For the blue function, the domain was 1 to infinity. which makes the range for the green one 1 to infinity. The range for the blue one was all real numbers from minus to positive infinity. Now the domain for the green one is all real numbers from negative to positive infinity. The vertical asymptote was x equals 1 for the blue one. Now the horizontal asymptote is y equals 1. So this is the effect of the fact that the two functions are inverse functions. So again, 2, 0 becomes 0, 2. We had 11, 3, now we have 3, 11. And the rest of this stuff as far as domain, range, vertical asymptote becomes a horizontal asymptote and vice versa. This concept. Solve logarithmic equations. Example 10, part A, log of 2x plus 1 base 2 is 3. So again, I go with the arrow and I say 2 cubed equals 2x plus 1. Two cubed is 8. Subtract 1 becomes 7. Divide by 2. You're done. You can check by putting this back into the original equation, meaning log base 2 of 2 times 7 halves plus 1. We have to check. 2 times 7 halves is 7. 7 and 1 is 8. Log 8 base 2 is 3. And we are done. Part B, log 343 to the base x is 3. Let's go with the arrow. X cubed is 343. You may know that 343 is 7 cubed, and therefore x must be 7. Two e to the power of 3x equals 6. Let's divide by 2, both sides. We get e to the power of 3x is 3. If we go with the logarithmic format, in this case, the base is e, so we have a natural log of this value, ln 3. And this is the base. This is e is the base, and this is the exponent. So 3x equals ln 3. Reminding you y equals ln x means x is e to the power of y. So what is x? Divide by 3. This is the exact answer, everybody. ln 3 divided by 3. You must always have the exact answer. And then if you use a calculator, however many decimals they ask you. And for example, if you want 3 decimals, you have to go to the 4th one to make a decision, okay? That's how the rounding works. According to scientific research, the percent of the course that one remembers after the conclusion of the course is approximated by the equation r of t equals 85 minus 41.9 log of t plus 1, for t being between 0 and 48. Find the percentage of the course that one will remember after 10 months. Basically, plug in 10 here. That's all it says. So R over 10 is 85 minus 41.9 log of 10 plus 1, which makes it log of 11. So this is log 11, and you have to use a calculator to find that. Multiplied by 41.9, subtracted from 81. And it gives you 41.3656. That's a percentage because they said percentage. So please understand, when you calculate this, you get 41.3656. Then you answer it with the percentage because they said it's a percent. Okay. So what percentage? 41.3656%. What about 25 months? Replace the T with 25. And it's 26. You have to calculate log of 26 multiplied by 41.9 subtracted from 85. Gives you this number, and then you change it to a percentage. What does it mean? So when we finish a course after only 10 months, again, assuming that we've done an A1 job, by the way. If we don't do anything about it, if we don't study, we remember about 41%. And after 25 months, a little bit more than 2 years, less than 26% remains in our memory. So these are applications. Example 12, pH of a solution. The pH represents the measure of acidity and alkalinity of a solution. A number between 0 and 7 indicates acidity. Lower numbers indicate stronger acidity. A number between 7 and 14 indicate alkalinity. Higher numbers indicate stronger alkalinity. According to this scale, a value of 7 represents neutrality like water. It is roughly the negative of the log to base 10 of the molar concentration measured in units of moles per liter of hydronium ion concentration, which is represented in chemistry by H3O plus. Sometimes they just use H plus, everybody, either this or this format. So pH, by definition, has the following formula: minus log of H3O plus, the hydronium ion. So find the pH of a solution whose hydronium ion concentration is given as such, 2.8 times 10 minus 3. All it means, all of this is about a piece of information from chemistry. So all you have to do, replace this with this number. That's all. And to be honest with you, you have to really put it into a calculator to come up with the answer. However, even if you don't have a calculator, you should be able to guesstimate what the number is and whether it's acidic or not, or basic. They say from 7 to 4, larger than 7, from 7 to 14 is basic, from 0 to 7 is acidic. So again, you have to put it into a calculator. But if I want to use it just the way it is, I'm going to show you the properties that it's coming up. Okay. You don't have to worry about these properties yet. We will discuss that. So minus log of this and this. You are going to use the product rule. So we are going to use log of this plus log of this. And log of 2.8, I don't know the answer. I need a calculator. But this one, because by the way, the base is 10. The answer is negative 3. So we have negative log of 2.8 minus 3. And if you apply the negative, you get this one, plus 3. Again, without a calculator, I want to discuss that. Remember, log of 10 is 1. So if it were 10, it would be 1, this would be minus 1, but it's not, and it's less than that. So this number for sure is less than 3, which makes it acidic because it's between 0 and 7. If you use a calculator, you get 2.55 less than 7, which makes it definitely acidic. And that's the idea. What I want to remind you, as far as the graphs are concerned, properties of logs. Here's f of x equals log x space a. When a is larger than 1, it looks like this. Domain from 0 to infinity. Range is all real numbers. You have an x-intercept at 1, 0. There is no y-intercept. You have the vertical asymptote, which is the y-axis or x equal to 0, and it's an increasing function. However, if a is between 0 and 1, so log x base a is between 0 and 1, everything is pretty much the same, except this is a decreasing function, meaning domain is 0 to infinity, range is minus infinity to infinity, x-intercept is still 1, 0, y-intercept, we don't have it, vertical asymptote is the y-axis or x equal to 0, and it's decreasing. So that's the main difference between the two. And this So this function and this function are inverse function, and they're symmetric with respect to the line y equals x. Now for this one, you have y equals a to the power of x when a to the power of x is negative, so it looks like a different color. So it looks like that. This would be y equals a to the power of x, where a is between 0 and 1. And symmetric with respect to the line y equals x. Just wanted to give you the properties of log functions.